Okay, so let's get started. Welcome everyone. This is online Spintronics seminar number 98. Our today's speaker is Professor Haiming Yu from Beihang University. He's an experimentalist working on spintronics and magnonics. He received his bachelor's degree from Peking University in 2006, and then he did his PhD at École Polytechnique in Lausanne in Switzerland. His work there on thermal spin transfer torque in magnetic nanowires contributed to the early research in spin caloritronics. And then from 2011 to 2014, Haiming was a postdoctoral researcher at Technical University of Munich in Germany, where he studied spin wave propagation in nanostructured magnetic thin films. Since 2014, then he has been at Beijing University, and since 2015, a professor in the School of Integrated Circuit Science and Engineering at Beihang University. His current interests are in magnetic texture-based magnonics and quantum magnonics. So the title of his talk today is Current Manipulated Propagation of Spin Waves in Antiparallel Coupled Stripe Domains of LSMO thin films. So with this, Haiming, please go ahead with your talk.
Thank you, Kirill, for the nice introduction. And thank you, and also Xin, for the invitation to this great spin talk series. Today, my topic is current manipulated propagation of spin waves in antiparallel coupled stripe domains of LSMO thin films. As you can see, this work was done in a group of collaborations. I think this work was mainly done by my former postdoc, Dr. Chenpu Liu, who's now with Professor Mingjun Wu at Colorado State University. The sample was grown by our colleagues in Beijing Normal University group of Professor Jinxin Zhang. And the MFM was taken in Tsinghua University in the group of Professor Chen Nan. The theoretical section was provided by Professor Lambert Dun and also Professor Jin Qiao in Fudan. And the sample structuring and characterization was helped by Professor Dapeng Yu, Professor Peng Gao, and Professor Lin Jiang's group. So my talk will be divided into 5 sections. I will start with a brief introduction of the background of the research and show a few key results of the experiments. And then I will provide more detailed information of the sample structure we study. And then I will show the experimental results on the spin wave propagation in the theoretical domain structures, followed by the theoretical modeling. We try to understand our experimental observation. At the end is an experimental demonstration of current control or current manipulate experiment. So first, introduction and key results. So in this work, we study spin waves, in particular the propagating spin waves. For the introductions of spin waves, I think previously in the talk series, I think Professor Hillebrands have provided very good introductions. For us, we are mostly interested in the so-called studying the propagating spin waves, which is coherent spin waves excite at one place and detect in second place. And we can probe its phase, group velocity, frequency, and the decay length, and so on and so forth. So there are quite a few review articles that students could learn in this about the background of the field. The field studying spin waves or magnons is can be called magnon spintronics, or sometimes magnonics. So this field has been studied for quite some time. In early time, I think there's even patent proposed by the group of Professor Pang Wang on spin wave logic. And also this is also very nice work done by Professor Schumacher and the group of Professor Hillebrand on the spin wave transistor. And more recently, there's also magnon transport, and particularly, I think, incoherent magnon transport with 2 platinum stripes. This is done by a group of Professor Van Bies. And also, for example, they're also studying spin waves, Doppler shift effects, using the so-called propagating spin wave spectroscopy, which is actually more or less the same technique we're using in this experiment to study spin wave properties in the magnetic domain stripe structures. So for spin waves, it's can, for example, interact with the domain walls. So in one way, spin waves can, drive domain wall motion. It was theoretically proposed early by Yan Peng, also Professor Xiangrong Wang, and they proposed a spin wave can provide angular momentum and drive domain wall motion. And more recently, there are experimental demonstrations on spin wave pushing domain wall motion. This is done by the group of Professor Liu Liu. On the other way around, the domain wall can also control spin wave propagation. And there are theoretical and also simulations works that demonstrate that spin wave can propagate in the domain wall structures, and due to different domain structures, you can find the domain wall move in different channels. And also there are experimental observations of the spin wave propagation within the domain wall channel, in very narrow channel, in the nanometers, and this is experimentally observed by the BRS technique, the group of Professor Haiming. And there are also spin waves that can propagate or interact with other magnetic textures. For example, the spin wave can be generated in these vortex structures, and it can observe the spin wave propagation using the X-ray spectroscopy, that you can see the propagation of spin wave from the vortex core to the edge of the vortex. And also there are also spin waves dynamics in the skirming structures, and also the if you go to the nonlinear regime, a very recent theoretical work predict that the spin waves can interact with the breathing mode of the skirming, and to generate nonlinear effects to generate the so-called magnonic frequency code. And even more recently, there are experimental observation of the frequency multiplication, I think with associated with the dynamics of the domain walls. So we study spin waves interact with one particular type of magnetic texture, which is the theoretical domain stripes. So we excite and detect spin waves by coplanar waveguide with microwave technique. And then we use electric current to manipulate the domain stripe alignment and to control spin wave propagation. So this is the typical spin wave transmission spectral we measured, and the x-axis is the applied field, and in this case is along the domain stripe direction or parallel to the spin wave wave vector direction. And the y-axis is the microwave frequency, and the color scale is the S21 parameter measured by the vector network analyzer. And then in this structure, because LSMO is a metallic structure, so sample and we apply electric current also along this K vector direction, and we can switch the domain stripe in different orientation and then control the spin wave propagation from on to off. So this is some main results of the experiments. I will come back with more details. So first, I will provide some information about this sample in material characterization. This sample we study is the LSMO thin film. This is actually not a new material that has been studied for many years. And this sample was grown by our colleagues in Beijing Normal University. I think they grow by the pulse laser deposition technique on a substrate of LAO. And the thickness is about 150 nanometer, and the width about 100 nanometer periodicity of this domain stripe structures. So in order to form the periodical domain structure, we first apply a magnetic field in the film plane, for example, with 150 millitesla, and then we turn it off. So there will be a static domain structure formed in the film, even at the no applied field. And this is taken by the MFM technique in the Tsinghua University. The LSMO thin film was grown on this LAO substrate, and this is a TEM image of the LSMO film on LAO substrate. That was taken by this high-angle annular dark field image by Ngao in Peking University. You can see it's a very nice crystal structure. LSMO basically is a perovskite structure with AO, BO2 structure. And very interestingly, if we form the domain, periodical domain stripes, the spin texture in the domain stripes are actually quite complex and quite interesting. It has been studied by some other groups, for example, earlier time by the group of Professor Kimura, and they have the micromet simulations, and they demonstrates that in the domain stripe structures, each domain is up and down, perpendicular to the film. But interestingly, if we look at the domain wall texture, it is not uniform across the thickness. If we look at the domain wall, for example, at the center of the thickness, you see the domain wall is more like a kind of a block type domain wall. But if you look at the surface or the bottom, it's more like a nail type domain wall. And this is the wall magnetization direction is different. So, but if you look at the center of the domain wall, you can see it's something like a kind of vortex spin texture. So it's quite complex textures even within the domain. So then we characterize the thin film of LSMO by the ferromagnetic resonance, and we from the frequency versus field measurement, we can extract the saturation magnetization of the film to be about 300 kiloamp per meter. And from the line width extracted from the FMR spectrum as a function of the frequency, we can estimate the damping by extracting the slope of the data, and we can get the damping is about 0.03. So it's obviously it's not as low as far from the value of the E, for example, but it's still reasonably good that we can see the transmission of the spin wave signals within, let's say, a few microns or up to 10 microns. So this FMR measurement was done in Colorado State University by the group of Professor Ming. So then I will show you the main results of the experiments. And the experiment data was taken by this so-called propagating spin wave spectroscopy. This is actually pretty simple. We have two micro antennas, typically coplanar waveguides, integrated on the thin film sample. And we connect these two coplanar waveguides to the pico probe with RF cables to port 1 and port 2 of the VNA. So we can measure, for example, spin wave excitation at 1 CPW and detect it at the second. We can also measure the other way around. We can measure the spin waves excited at the CPW2 and measure CPW1. So we can measure the spin wave and then reciprocity effects also using these tools. So then we use this technique to measure the spin wave transmission signals S21 on this theoretical domain structures in this LSMO thin film. So actually, this is the data I showed you at the very beginning of the presentation with the zoom in of this mode. This full scale of the spectrum was the first set of data we measured on these samples. At the beginning, when students got this data, actually, we were quite confused because normally when we have regular magnetic thin films, we expect to have something like P-tail modes. It's more like if you have an increasing magnetic field, you have this like, two branches. Actually, we do see this P-tail modes vaguely, but interestingly, at low field regime, and we can observe a quite prominent signal at fairly high frequency, about 10 gigahertz. So this is a bit surprising to us at the very beginning. So we try to learn what is the origin of this high frequency mode. So with the help of our colleagues in Tsinghua University, we managed to take the MFM image of the samples by sweeping different magnetic field. And we find this high frequency mode only survives between, let's say, plus and minus 50 millitesla. And this is almost the same field region that the magnetic domain stripe structures appear. So if you have a applied field, let's say over 100 millitesla, the film will be saturated in the film plane, and there's no domain stripe structures, and certainly we do not observe this high frequency mode anymore. So if we look closely to this high frequency mode, if we take, for example, the line plot at 0 magnetic field, and we can see there's oscillation in the spin wave transmission spectrum. This is due to the phase oscillation probed by the vector network analyzer. If you consider this two peaks, it's a phase change of 2 pi. And if we extract the frequency span between these two peaks, we can, using a simple formula, to estimate the average hoop velocity, which is about 2.6 kilometers per second. So this technique was not actually invented by us. It was used previously by, for example, the group of Professor Bio, and also the group of Professor Grundler in their experimental studies, and other groups as well. So with this technique, we can estimate that this mode propagate in a fairly high velocity compared to a regular Pickel mode in this thin films at low frequency. Then we try to understand more what is the origin of this high frequency mode. So we return to a relatively simpler experiments where we put this film upside down, like pressure on a big coplanar waveguide structure. And then we select flip chip FMR measurements to measure this so-called spin wave reflection. And here we can also see clearly two modes: one low frequency mode, more like a regular Pickel mode, and the high frequency mode, which is also quite strong. And then we try to use the micromagnetic simulations to further analyze and to understand these two modes. And we use this ohm simulation, and we can fairly well reproduce these two modes in the simulation result, although there are more, there are richer branches, but in general, there are two modes appear. One is a mode that's low frequency around 2 gigahertz, and the other one is around 8 gigahertz. And then one advantage for using micromagnetic simulation is we can really probe which these modes come from in the our sample structure. So with this, we first look at the domain wall spins, or domain wall magnetizations at the wall. So this is also previously studied by other groups. So we look at this domain wall dynamics, and we find in simulations that they mostly appear at the low frequency branch. And then if we look at the domain, but more or less the domain surface part, these spins contribute also in simulations at the low frequency part. But if we look at the domain volume or domain core magnetization dynamics, we find they appear mainly at the high frequency branch. So this tells us this information that this high frequency mode is somehow related to the domain volume magnetization dynamics rather than the domain wall magnetization dynamics. If you look at the domain volume, it is basically quite strict up-down theoretical orientation in this domain stripe structures. And then we try to see in the simulation, how does this high frequency mode propagate in comparison with this low frequency regular mode. And we find that if we hit this high frequency excitation, we find this mode somehow propagates indeed mainly in the domain part. The wall part there has a relatively weaker signals. But interestingly, if we look at, for example, the up domain, the spin wave intensity somehow goes towards the upper wall. And the down domain, the spin wave propagation kind of tilted to the bottom wall. So there's some kind of asymmetry in the propagation from the simulation results. So we do not investigate too much in this, but we suspect it could be related somehow with the some chiralities in the domain wall structures that I introduced earlier in the simulations. So this is basically simulation results that provide some brief insight on these modes. But what are the main physical origin of these observed high frequency and low frequency modes? This kind of puzzles us for quite some time. And recently we have read some very nice work, very recently published, I think by the group of Professor Bayu. I think they provide some very insightful and very enlightening explanations that these two modes could be considered as Higgins and Goldstone magnon modes. If you consider the magnonic band structures, you can see this one in low frequency, one in high frequency. They have this particular two modes, and these modes goes down with higher wave vectors. And the low frequency mode, in their case, they are mostly in their drawing, there's a vortex. This is more like the war part, domain war part. And the high frequency ones, they're more like focused on the domain volume part. So this is consistent with our experimental and also simulation works. So this is, we have learned quite a lot from this new paper published. But initially we have hand waving explanations on our observation, provide quite empirical theoretical modeling. In this case, we consider this two domain stripes. One is up, one is down, and these two domain stripes, they align theoretically. So if we consider these two domains, which is about 100 nanometer wide each, they have some coupling between these two domains. So their dynamics will be related to each other. So we write these two dynamic equations for the M up and M down with an additional term of this so-called J up down, which is the coupling between these two domain structure. And if we solve this equation, we can have this spin wave dispersion like this. If we simply consider, this is the K is the spin wave wave vector. So if we simplify it, if we consider, let's say, a uniform excitation with K equals 0, then this equation is very much like a classic, antiferromagnetic resonance equation, except for the HE, which is the effective, which is the exchange field, that is the exchange field between two sublattices in the antiferromagnetic materials in atomic scale, which is normally very, very strong, probably in the regime of let's say 100 Tesla, even stronger. But in this case, we have this term replaced by the H effective up and down, which is related to the coupling between these two up and down domains in the scale, length scale of 100 nanometers. So it's much weaker. That is also why that's the antiferromagnetic resonance normally goes to terahertz, but this mode goes to about 10 gigahertz. So from our experimental data, we can try to use this empirical formula to fit our experimental data, and we can extract an estimation of this H effective up and down to be about 0.55 Tesla. That is about 2 orders of magnitude smaller than the typical antiferromagnetic exchange coupling. We take a value, for example, is this MNF2. So it's about 2 orders of magnitude smaller. That is why these modes are not at terahertz or 100 gigahertz, but rather at about 10 gigahertz. So you can consider this as an effective antiferromagnetic spin wave mode. So the coupling between the up domain and down domain, so the strength is not so strong. So what is the origin of this coupling? So first we consider that the dipolar coupling between this the up domain magnetization and the down domain magnetization. So we have a very simple estimation. This is done by Professor Jiang Xiao in the paper, and then we can estimate that the dipolar coupling effective field between the 2 domains, up and down domains, the strength is about, let's say, 0.11 Tesla. So it is weaker than the value we fit, but at the same order of magnitude. So we believe the dipolar interaction between 2 domains definitely contributes, but probably maybe not the purely by dipolar interaction. There might be also the coupling of the dynamics of the 2 domains through the wall textures. That we didn't calculate, but that could also contribute to the effective coupling between the 2 domain dynamics. So at the end, we try to provide a demonstration of the current control experiment in the spin wave propagation in this theoretical domain structures. I think first step, we try to realize the fields control. That means at the beginning, I mentioned that these domain structures can be formed by applying an in-plane magnetic field and turn it off. So we can apply the field in 0 degree, and the domain stripes lies in theta equals 0. And we can also apply field in, let's say, 30 degrees, 45 degrees, 90 degrees. So domain stripe will align accordingly. And this field is applied by 150 millitesla for 1 second. And then we try to measure the spin wave propagation in this domain structures with different alignment. And we find when the spin wave propagation is along the domain stripes, we have quite large transmission signals, as we discussed. But when it's tilted away, it gets smaller. And if the domain stripes lies perpendicular to the spin wave propagation direction, or in other words, perpendicular to the spin wave vector, then the signal almost disappears. This could be understood because the spin waves will hit multiple domain walls and could lose its energy. And also these modes we find in the high frequency mode prefer this theoretical up and down structures at their excitation. So they favors the theta equals 0 orientation. And then we try to then use current to control the spin wave propagation, because this is more flexible and also more easily integrated into a device. So here we make a whole bar structure where we can apply a current pulse. And here we initialize the domain stripe structure by applying an in-plane magnetic field in plane, say along the x direction, and we can see from the MFM that the domain stripes are in general lie in the applied field direction. And then we apply electric current also in x direction. This is a current pulse for first with 10 milliamp, and we can see the domain stripes does not change very much. And at the same time, we measure the spin wave transmission. Also, spectrum doesn't vary much. And then if we increase the applied current value to about 20 milliamp, we can see again the domain stripes almost remain unchanged, and then we can see the transmission is still quite pronounced. But if we apply current up to about 25 milliamp, and suddenly it switch about 90 degree perpendicular to the current direction. And then if we now probe the spin wave transmission, it's the transmission signal decreases dramatically and almost cannot be seen. And interestingly, this critical current we use to switch or reorientate the domain stripe alignment is only about 1.7 times 10 to the 5 amp per centimeter square. This is quite low compared to a conventional spin transfer torque critical current density. So we're still quite thinking, so what is the real mechanism of the switching in this complex domain stripe structures? We have done some additional measurement to give a little bit more insight or information for us to understand it. So we make it like a disk of this LSMO, and then we have a electrode put on different directions. And again, we first align this domain stripes in each directions for the initial states. And then we apply currents in this yellow arrow direction, and we can see that the domain stripes switches are quite different. So in general, it has some kind of anisotropy in terms of the switching behavior. So we're still trying to understand what's the key mechanism of these switching behavior. Well, because LSMO is a conductor, it could be related to spin transfer torque or spin orbit torque. So, and also very lately, we also learned from the literatures and also from some talks, it may also potentially relate to some new mechanism of switching. For example, what is so-called self-torque. This is a new results. I think it's from the group of Professor Furt. You have one single magnetic materials, I think it was gadolinium iron cobalt, if I didn't remember wrong. They apply electric current in the single materials, and they have the generated torque, what they named as a self-torque. And also, since LSMO has also clear AMR, and we recently learned that the so-called planar Hall torque is kind of a reverse effect of AMR. So we don't. We also suspect it may potentially related to this effect that was, I think, was discovered by the group of Ilya. I think, but this is still open for the switching mechanism. So we're in future also trying to do more systematic work. And we have, at least from sample growing technique, we have one more progress that we can grow LSMO on the NGO substrate with much more straight domain stripes than before. So it's very well defined with the alignment and also periodicity. So we're in the future working on these LSMO samples on the NGO substrates and hopefully get more insight of the switching mechanism. So with this, at the end, I would also acknowledge some people who really did all this experimental work, particularly Dr. Chenpu Liu, who is now at the Colorado State University, and he did most of the measurements, and also Jianyu Zhang, who actually he had his PhD defense this afternoon, Beijing time, and he's technically he's a doctor, so he did most of the sample preparation with device structuring and so on. Also, also thank my former PhD Tobias Strickler and former postdoc Dr. Florian Hambach, who helped build and also optimize the microwave setup. At the very end, please let me do allow me to do a little advertisement that we have an IEEE ICMM conference 2020 supposed to be in Beijing, but due to the COVID situation, it will be fully online. This is the 7th IEEE International Conference on Microwave Magnetics after the success of Fort Collins, Boston, Kaiserslautern, Sendai, Tuscaloosa, Exeter, and then in 2020 it was supposed to be in Beijing, but due to the outbreaks in Wuhan, and so it was proposed, it's canceled, and now in 2022 still it's difficult, so we have it fully online. But now we have all invite speakers confirmed. So we will encourage and welcome you and to participate. There's no registration fee. If you're interested, please register via the conference website, icmm2020.cn, which is the one we registered for the 2 years ago. So with this, I would like to thank you and very much, and thank you for your attention. Thank you.
Thank you, Haiming, for this very interesting talk. We can now take questions. To ask a question, please raise your hand in Zoom, or if you're on Twitch, just type your question in and I'll read it for you. So, Shin, please go ahead.
Thank you very much for this interesting talk. I have one question about I think it's on slide 17. And you did a flip chip measurement of the spin wave reflection. Are those coplanar waveguide also have the same very tiny separations?
No, actually, these are very big ones, really, say a millimeter size, so larger than the sample. So they are more uniform excitation.
Oh, I see. I see. And another question is, can you remind me what is the domain wall size? Oh, like the periodicity of this domain wall.
So the domain wall size is about 100 nanometer. So if you count up domain to another up domain, that's the periodicity is 200.
Right. I see. And you refer to this this mode as like the antiferromagnetic-like mode, which antiferromagnet, it's the exchange coupling constant is negative. But in your system, it's still a ferromagnet. So strictly speaking, the exchange coupling is still a positive number, right? So it just feels to me, and the reason it forms antiparallel configuration is to minimize the dipolar energy. So it feels that
right.
coupling is still dipolar mediated. But I guess you also did the estimation that dipolar field is not strong enough to boost that high frequency mode. So that's actually quite interesting. I haven't.
Yes, it's a very good question. Yeah, it is indeed a ferromagnetic material. So if you consider the next neighbor spins in the atomic scale, it is a ferromagnetic exchange. That's for sure. This so-called exchange coupling between these two domains are kind of effective exchange or effective coupling. Not necessarily exchange. But I think the dipolar definitely favors to be antiparallel for these two.
Right.
And there for the dynamics, through the complex domain wall structure, which is if you see the cross section like a vortex. So I don't know how this would contribute to the dynamics of these two domains. So it might need more investigation.
Sure. Yeah. Thank you very much. And also, just one last question is this kind of dipolar coupling, unlike the exchange coupling, is maybe exchange coupling can be more isotropic. That means whichever direction is always positively coupled and negatively coupled. Like dipolar interactions, maybe your overall moment is favors the antiferromagnetic coupled, but when you do the precession, the x and y directions, do they also favor the anti-parallel coupling, or do they actually favor parallel coupling?
This is a very good question. You mean the deviation from the
because it's a dynamics, right? So the precession coupling the x direction and y direction will be more important than the coupling in the z direction, I guess.
Yeah, it's a good question. I need to think about it a bit more, but by gut feeling it will have a maybe favor anti-parallel MX and yeah.
Thank you. That's all my questions.
Thank you. Are there any other questions? Let me ask in the meantime. So in these pictures, like the one on the screen right now, there seems to be something like a cut at about 10 millitesla or a little less.
Right.
What's the origin of that? You have that in all pictures, and it's asymmetric. It's always a positive field. What is it?
Yeah, it's a very good question, a very sharp observation. Yes, it appears both in simulation and also in experiments. From at this point, my conjecture is that this related to some kind of switching within the domain wall structure, because let me quickly go to the simulation of the domain wall. So because the domain wall structure has a core that is pointed either out of the screen or inside the screen. So with a small field sweeping in these directions, maybe the whole domain stripes appears the same, but the core may switch at the very small high field. So this is our our guess at the point.
So would this be hysteretic if like you change the field in the opposite direction?
Yeah, there is a small hysteresis. Yeah, there's a small.
But why is it not symmetric with respect to zero field? There's like a bias connection.
Yes, so if we sweep the field from so now it's always from negative to positive. But if we sweep the field from positive to negative, it's kind of symmetry.
Oh, so you always sweep in one direction only.
Yeah, so yeah, for the comparison.
I see. Okay. And the other question I had is, so here, in all of those measurements, you have perpendicular anisotropy, right? So have you thought of whether it will be different if the anisotropy is in plane?
Well, these samples, in fact, Kirill, if we see the VSM magnetization loops, they are not like typical perpendicular magnetized films that have a very nice squares for the hysteresis. They remain a large autoplane magnetization at zero field. Because if you have a total magnetization autoplane, it's nearly zero. So it can be very easily saturated in plane. But if we try to pull all the magnetizations autoplane in one direction, it needs very large field. So to go against the texture, so very large field. So it's at low field. It's the domain stripes definitely align autoplane for up and down. But it's not like a typical PMA material have a saturation perpendicular magnetization. So it's for us, this is a bit special in this case.
So why are they aligned perpendicular then?
Yeah, it's a very good question. Yeah, so I think it's a total energy somehow favors this spin texture as very low field. And it can be broken by applying 50 millitesla very easily. So the generation of the texture, the origin of the texture, there could be several mechanisms. One of them could be the strain, at the between the RAO and LSMO could provide some initial force to generate the spin alignment, in the magnetic material, but this is not,
But you have micromagnetic simulations, right? So to get this kind of texture with perpendicular spins, what do you need to put in?
I think the one major also the mechanism was a dipolar interaction. So the integration of the dipolar interaction over a certain thickness, at certain thickness kind of favors these textures to minimize the total energy. So if the thickness is very thin, you will never, not easily have such textures. And if it's very thick, again, also not very likely. Only in this, putting in this parameters of LSMO is about 100 to 150 nanometers in this region.
Interesting. Okay. So any other questions in Zoom or in Twitch? Let me check there. Doesn't look like it. So let's thank Haiming for this very interesting talk. You can use the reactions buttons.